So welcome to part 2 of lecture 9, and now we are going to talk about factor models. So that's the agenda, introduction, model setup, estimation, and the choice of the factors. The references are exactly the same as in the previous block. Okay. So let's start with some motivation, some toy example. Okay. So how can we motivate of a factor model? Think a little bit about what's a factor. What do you believe is a factor? Okay? That's something that we can discuss during our live session on Friday, but it's a very important question. And how factor models will differ from what we saw in the first block of this lecture. Okay? So basically we can say that a factor will be present whenever there is a large number of variables moving together. We can consider different assets, for instance, and look at asset returns. Okay? Suppose that we want to model n stocks in the stock market over t periods. Okay? And for every stock I at time t, we want to model the return, RIT. And based on what? Based on the return of all other stocks in the market. So we define this R minus IT as the returns of all the other stocks in the market apart from equity I. Okay? So we can think about a linear regression, like regressing the return of stock I on all the other returns. Okay? So that's a possibility. However, we have a large dimension set, and we can of course use lasso here, but lasso, what lasso will do, lasso by construction will induce sparsity. Okay? And suppose that we don't have sparsity, that for instance all the returns matter. Lasso maybe is not the best alternative. Okay? So how can we estimate the parameters of the model? If n is less than t, of course we can do OLS. N larger than t, we need some regularization. Ridge won't give us consistent estimates, and lasso will give sparse solutions, as I mentioned. But should we expect the betas to be sparse? Is sparsity a reasonable assumption here? How can we overcome these restrictions of sparsity? Of course, we can use elastic net, but still, although we allow for more variables than observations, elastic net still induces sparsity. Okay? So what we know is that the stock market tends to move together, and sometimes in opposite directions. Okay? So it is as if there is a latent variable, let's call Rm, driving the whole stock market. Okay? So we may write a model that RIT equals to a fixed effect, mu I, plus alpha I Rm, this driving force that are making the market to move together. Okay? In that case, if we assume that Rm and U, the covariance is 0, then we can show that the covariance between two different firms, the returns of two different firms, will be given by alpha I, alpha j, sigma squared. So if we run a regression of Ri on all the other returns, this model is not sparse by construction if we believe there is a driving force in the market. Okay? And so we expect the beta ij to be 0 only if either ai or alpha j is 0. Okay? And this is the KPM. That's the capital asset price model, where you have the most famous, that what's RM is the return of the market. Okay? So under the KPM, a regression among returns cannot be sparse. Okay? So sparsity does not seem to be appropriate here. Okay? we might be able to justify sparsity on the covariance structure of U. Okay, in other words, expect almost off-diagonal terms in the NN matrix omega 0. What's this matrix omega? Is the covariance of the U's. So what we can say is that after we remove the factor, okay, the remaining idiosyncratic returns, okay, they are almost uncorrelated. Okay. And this is called the conditional sparsity. Okay. Condition on the realization of the common factor, we have sparsity. Okay. So what we are going to call factors. So we are going to take this example and expand this example. So basically we say that there is a few latent drivers for co-movement of a large set of observable variables. Okay? That's the key idea. Okay? And the relationship between the factors and the axis is not deterministic, so we may include an error term. So basically you're saying that x is a function j of f, these latent driving forces that we don't know, we do not observe, plus a random component. Okay? So in conception it's similar to PCA, okay? But here's the main difference. PCA is a tool, it's a computational tool to reduce dimension, and factor models is a model, and it's based on assumptions on the data. So you saw that during the first block I made no assumptions whatsoever. Okay? To justify factor models, we have to start making assumptions because it's a model, it's not a tool. Okay? And there are several variants of factor models. We are going to look one specific, and they basically differ from each other on the structure of the pair f epsilon, the factor and the error, and the functional form of this function g. Okay? So the function can be linear, non-linear. Of course, we are going to focus on linear. Non-linear factor models is a much more complicated issue. Okay? The structure of the factors, they can be static, so x depends only on f at the same point in time, so that's why it's static. Dynamic, x depends also on lags of f, so the lagged factors also influence the dynamics of x. And also we have hypotheses on the structure of the idiosyncratic shocks. Exact factor model, the covariance matrix of epsilon is diagonal. Okay? The non-exact factor model, the covariance matrix of epsilon has non-zero off-diagonal elements. Okay? And we can also allow for temporal dependence on the epsilons. So let's focus on a linear static factor model. That's our model for today. So basically say that each xi is modeled by a fixed term, the fixed effect term, the constant, that depends on each, it differs for each cross-section unit, okay, plus the effect of k factors, latent factors, plus the noise. So this is what we call the idiosyncratic error, okay. So this is the common factor structure. This is the fixed effect. Okay. So these coefficients B are also called the loadings of the factor model. Okay. And one thing that's important, we are considering the factors to be unobservable. Okay. And as I already said, the epsilons are the idiosyncratic shocks. Okay. In vector form, we can write xt equals to mu plus bf plus epsilon, okay, where x is an n-dimensional random vector, mu is a n-dimensional vector, b is an n times k loading matrix, and epsilon is a zero mean idiosyncratic shocks vector. Okay, and what we want to do, we want to identify mu, b, and f. The question is, can we jointly estimate these three quantities without any further assumption? And the answer is no. We need restrictions, we need assumptions, otherwise we don't have identification. Let's refresh our memory about identification. We said that a parameter theta is point identified by a distribution, a model, P of theta, if theta 1 differs from theta 2, then P theta 1 will be different from P theta 2, okay? Or equivalent, if P theta 1 equals to P theta 2, then it means that theta 1 equals to theta 2. So the model cannot take the same value, the probability model cannot take the same value if there are two different thetas, okay? Why do we care about identification? Well, if we not, how can we estimate the model from the beginning? We need to estimate the parameters, and we want to estimate parameters that make sense, okay? So we want to first, before estimating a parameter, we have to determine under which conditions this parameter is identified by our model, okay? So let's go back to factor models. Can we point identify mu in our factor model? Bad news, not really, because even if we knew the loadings, we do not know the expected value of the factors, the mean of the factors. So the expected value of x is mu b times the expected value of f plus the expected value of epsilon. Of course, the expected value of epsilon equals to 0, okay? So we have the expectation of x is mu plus b expectation of f. So if we change mu to mu tilde, the mean of x could be unchanged, because this change can be compensated by a change on the expected value of f. So we have to impose a restrictions, so in order to make sure we can identify mu. So what we do, the first restriction that we are going to impose is that these factors, these latent factors, have all 0 mean. And in this case, mu can be identified by the expectation of x. So mu will be the mean of x. Okay? Is this assumption without loss of generality? Yes, because we can write a new f minus plus the expected value of f will be a f tilde plus the expected value of f. So redefining factors, okay? So this factor here will be the d mean factor, okay? And this term here goes into mu, the new mu, okay? So we are fine, okay? We remove the mean of f and we set it to mu. Okay, so good, mu is identified. How we go on identifying f and b, okay? And we can do it without assumptions? Not really, because any non-singular k plus k matrix H, we are going to have x equals to mu plus bf plus epsilon equals to mu b. I'm going to multiply and divide by h f plus epsilon. So we have like mu bh f tilde. I'm going to call this f tilde. Okay? So we can not really identify, and the covariance matrix structure will be given by sigma, and that will be the bh expected value of this new factor, the new factor transpose h transpose b, plus bh expected value of f tilde epsilon. Okay? So that's the covariance structure of x. And so how can we try to identify these coefficients, what we are going to do, we are going to assume that the factors are uncorrelated with the error term. Okay? So basically, this term here, these two terms here will be equal to 0. So then the covariance structure will simplify to that expression that you see on the slide, okay? So that we can choose an orthogonal H, okay, such that the variance of inverse H F will be identity. Okay? So then we have sigma will be given by B transpose plus omega. Okay? So what we are going to do, basically we see that we can have, if we multiply by any H, we can get exactly the same model. So now we have to restrict to which H we are going to look. So the first thing, we want an orthogonal H, okay, such that we get this expression on the slide. So does such an H all exist? Do we need any condition here? It will always exist because the variance of this F tilde is positive definite and admits a spectral decomposition. So it looks like a lot of technicality, but what's the message here? The message here is that, in fact, we cannot identify the exact factors that lives in the nature. Okay, so if you assume that the true model is a factor model and there are kind of the true factors, we will not be able to identify these true factors. We are going to uniquely identify a factor that's a very specific rotation of the original factor. What we are going to identify is this F tilde, okay, that will be equals to H minus 1 F. Okay? And this F tilde will be also zero mean. Okay? This object we will identify. Okay? So, and there will be a single H that will be given by exactly the spectral decomposition of our covariance matrix. Okay? So, under the identification assumptions, we have that the covariant matrix of X is given by this expression, okay, where B prime is a low rank matrix and omega is a full rank matrix, okay, but can be sparse. But now, okay, we can identify this F tilde, but we need B. So if we have F, we can identify B. If you have B, we can identify F. But how can we do both? So it's kind of chicken and egg problem. Okay, how we simultaneously get the loadings and the factors. Okay. So because, as I said, if we knew F, then we could estimate B. If we knew B, we can estimate F. So the solution, everything together. And how we are going to do that, we are going to minimize this expression that you see, the Q. Okay? So we want the set of K factors, okay, or N factors, if you want all of them, the K factors, we want to minimize this sum of the squared errors over the cross-section over time. Okay? And we want to find a solution for the problem. So if we know the factors, okay, the solution for the B's is just an OLS. The problem is that we don't know the factors. Okay? But if we use the normalization, another restriction, that F prime F divided by T equals to identity, we get this objective function, okay? And we can show that this function is the Frobenius matrix norm, okay, of this matrix here, okay? And we just need to find minimizers for that. The good thing is that when you try to find minimizers for that, we get exactly the same optimization problem as PCA. Okay? So this is exactly the same problem that motivates PCA. So basically the factors are nothing more than the principal components. Okay? So the minimizers of R of F is equivalent to maximizers of the trace of this matrix F prime X prime XF, subject the factors to be orthogonal. Okay? So if we define, to make it more evident, we can define gamma equals to F divided by square root T, and noting that sigma X prime X divided by N is the T plus T sample covariance matrix of X, the problem is equivalent to maximizing gamma sigma gamma subject to gamma prime gamma equals to 1. This is exactly PCA problem. Okay? So we can find the factors by computing principal components. This is just the proof. I'm going to skip that. Okay. So to estimate a factor model, basically we run a principal component. Okay. So if we want to avoid unitary vectors, you can make this transformation. So the true factor will be square root T times the matrix of the principal components, and the loadings will be given by X F hat divided by T. Okay. What's some important remarks that we had to make? What's the difference between static and dynamic factors? This is not a sharp difference. We can also write a dynamic factor as a static one by including more factors. Okay. A static representation involves different factors, but we may not care because are the factors real or just a dimensionality reduction technique? Okay. That's an open question. We can discuss that more during our live session on Friday, but that's the key. How do we give interpretation for this factor model? What are these principal components, right? Can we give an economic meaning? Okay. And the other point is that it's not really possible to allow a lot of cross-sectional dependence on the idiosyncratic shocks. Okay. So we need that the omega matrix to be almost sparse. Okay. We can allow for time series dependence, but it cannot be very strong on the absence. Okay, so basically saying that most of the dependence, either on the cross section or in the time series, will be driven by this set of factors. Okay. Factor models versus variable selection. Basically, should we do lasso or factors? Can we do both? That's something, another point for you to think about, that we can discuss on Friday. How can we reconcile factor models and sparse regressions? Can these two things live together, or they are opponents for life? That's something that I want to discuss with you. Okay? How we should choose the number of factors? We can do exactly the same as in the case for principal components. Okay? And use the same techniques. There are a bunch of other ways, or use like information criteria. Basically, we are going to look at the IC will be the fit of the factor model plus a penalty that depends on the dimension of the problem and the number of factors. Okay, and we want to minimize the IC. So the number of factors will be the value that minimizes the IC, okay? And there's this resultant Bieneng showing that if there is a true number of factors using the IC, we can asymptotically find the right number of factors, okay? And there are a number of penalty terms, okay? And where this CNT is the minimum between square root n and square root t. Usually in practice, you look at all of them and see if there is some divergency. Usually, in my experience, they all converge to the same number of factors, okay? Although Bieneng say that the second one, G2, gives more stable results in empirical applications, okay? And so that's it for today, and I see you on Friday. Thank you.